Hello, everyone. My name is Yuvit, and our project is utilizing autonomous drones to identify fire hazards near power lines in remote areas. We're in McMahon's AVY group, and today Niru, Ronil, and I will be presenting. However, the other members of our group are listed here. Next slide. Okay, so what's the problem? As many of you would know, California, along with other states like Texas, have been experiencing a huge amount of wildfires over the last few years. A large portion of these fires were caused by the electrical distribution system, primarily issues regarding power lines. Over the last 3 years, Texas experienced over 4,000 wildfires caused solely by faults in electrical distribution. The Paradise Fire, caused by a tree falling into a PG&E tower, burned over 80,000 structures. We can clearly see that something needs to be done regarding the risks surrounding power lines. So you might be wondering what all of this means and why is it necessary? Well, we aim to identify fire risks to power lines. Uh, for this, a drone would be beneficial. Our goal is to prevent dangerous wildfires such as those we have in California and have been experiencing in recent years from PG&E and other electrical utilities company. So there are many risk factors we plan on training our drones to look out for. A few examples may include unstable trees or brush that can catch fire immediately if a power line or spark were to fall. Another common cause for fires are arching conductors, meaning the discharge caused when electricity flows through conductors. In this case, the power lines. Finally, some other risk factors that we'll have to consider include invasive vegetation, animals such as birds, and damaged or loose components. The first key risk factor is surrounding trees. Trees often fall over due to high wind and poor stability. We often experience the effects of this, like power outages and network problems caused by trees falling on power lines. However, the problem is twofold when a tree falls onto a power line. Electricity continues to flow through the line, leading to something called arching, or when the high voltage conductors on the power line and the vegetation on the ground, like trees and shrubbery, form a path for electricity to flow through. This often leads to the branch or shrubbery lighting on fire, possibly creating the beginnings of a forest fire. While most other projects focused on the distribution poles themselves, our project will focus on the surrounding vegetation. It will use high-resolution images and possibly infrared scans to assess the stability of nearby trees. This is important to make sure that they won't collapse onto a nearby power line during high winds or other unstable conditions. Invasive vegetation could create a short circuit or damage the poles. Now let's talk about why we decided to use drones to accomplish our goal. Even though power lines can be inspected manually and have been inspected manually for the longest period of time, the process itself is extremely difficult to do in remote locations. By using drones, we can inspect more power lines in the same time it takes to inspect one manually. Furthermore, the drones can assess remote places that are difficult to reach manually.
So there are a couple efforts that other companies are currently doing. So PG&E's wildfire safety programs and initiatives focus on reducing the potential for catastrophic wildfires related to electrical equipment, which would reduce the potential for fires to spread. The RIDI program enhances the evaluation of SDG&E's overhead electrical power lines and equipment within identified high fire threat district areas. Xcel Energy has committed to investing in and using drones or unmanned aircraft systems, UAS, to inspect its electrical and natural gas systems. The company inspects more than 320,000 miles of electrical and natural gas infrastructure to ensure the safety and reliability of its energy system. EPRI explores using autonomous drones for inspecting power lines and other utility infrastructure. This can improve efficiency and potentially safety by reducing the need for workers to physically climb structures. SCE's wildfire mitigation program seeks to reduce the risk of harming wildlife while repairing utility infrastructure like power lines. So these are all basically just the past and current related projects.
So now I'll start talking about the hardware and more technical stuff regarding our project. So as we said previously, we're going to be using a drone kit, and the drone kit we're going to be using is the Holy Bro. So we have other parts as well. We have a LiDAR camera, which is used to accurately detect vegetation and power lines. The Raspberry Pi will make our drone programmable and give us something to run our identification algorithm on. A GPS will be used to keep track of the current location, and they're going to give us geotagging data and ensuring the drone can follow pre-planned flight paths accurately. The flight controller is essential for stabilizing the drone and executing flight commands, including autonomous flight and data collecting missions. Our receiver, which is the radio master, is required to communicate with the remote controller, which is allowing us to test out the drone before we let it go autonomous. The telemetry radio allows real-time data transmission between the drone and the ground control station, enabling live monitoring and adjustments during flight missions. So we're going to be using lithium ion batteries, and those batteries are necessary to power the drone and the remote controller. So now I'll start talking about our drone kit specs. So this is the Holy Bro X500, and the reason we chose this specific drone is I think we were debating on other drones. We like this one best because for efficiency, expendability, and also the cost. So right here you can just see some of the statistics of the drone. And one thing that we were looking at was that flight time. That 18 minutes is really essential. A lot of the other drone kits we were looking at were less than 18 minutes, meaning that like we would have less time to cover the ground. So this is our current state of the drone. So what we've been doing so far, we've already put together a basic framework for the drone, and we're adding additional parts such as a camera and LiDAR camera. We have added the lithium ion battery and currently working on the communication system. So we're currently working on like the radio and the flight controller to help us test out the drone before we let it go autonomous. And we're using Q ground control, which is software that helps us keep track of the drone at all times, and are working to connect our software to connecting the drone to the software. So now I'm going to be talking about software. So our methodology employs a drone-based system to identify potential fire hazards in areas surrounding power lines. So we're going to be leveraging Raspberry Pi, as we said before, equipped with a camera. We're going to be using advanced object detection to identify power lines and nearby vegetation. So our methodology for fire hazard detection using drone technology. So our approach employs a drone equipped with a camera connecting to a Raspberry Pi to monitor power lines and surrounding vegetation. So the first step is data acquisition and pre-processing. The drone's camera captures real-time video and still images, which are streamed to the Raspberry Pi for immediate processing. The use of OpenCV, or open source computer vision library, allows us to pre-process images, including filtering, contrast adjustments, and edge detection, which enhance object detection accuracy. So specifically for that object detection, we're going to be using TensorFlow and Object Detection API, where our system identifies critical objects such as power lines and nearby vegetation. A pre-trained model fine-tuned for vegetation and power line detection is deployed onto the Raspberry Pi, and TensorFlow's optimized models for edge devices enable our system to run efficiently on limited hardware while maintaining high accuracy. So for distance calculation and fire hazard assessment, once power lines and vegetation are detected, OpenCV's geometric transformations and perspective analysis tools are used to calculate the distance between these objects. If the distance falls within a predetermined threshold, the system flags it as a potential fire hazard. These calculations utilize trigonometric analysis. And the last thing is real-time hazard reporting. So the process data and hazard status are transmitted to a central monitoring dashboard via using our radio, and this will give us real-time notifications.
So, current method that we're considering is this kind of red flag method. So basically what we do is we select specific relevant data sets, and then our data will be grouped into two parts. So one part will be trees intersecting power lines, and the other set will be like trees a safe distance away from power lines. So in each of these in all of these images, we be labeling relevant features in the images, such as intersecting branches that are a good distance away, power line components, etc. So we plan to train our machine learning model on thousands of pictures of unstable trees, invasive vegetation, and etc. So we're gonna basically have like 75% training data and 25% testing data. And overall, this model will identify the risk to the power lines. So when the drone discovers a photo with like a hazard in it, it'll like flag it as a tree intersecting a power line, and it'll say the coordinates, pole number, or other identification. So local authorities can locate the hazard and determine whether or not, like, how dangerous it is. So some specific things that we'd be looking at in these photos are dead trees. So you can tell like when they're starting to rot and etc. And we're also going to be looking for gaps within branches, like V crotches. And we'll also be looking for decay, usually closer to the bottom of the tree. We'll be looking for larger cavities within the tree, hanging branches, and some trees lean toward it's like the sun to get a better access to it, which make them really unstable and potentially dangerous. So in our images, we kind of want to flag these so we can make sure that our machine model knows that that's what like a dangerous brush looks like.
So I'm going to continue talking more about the distance measurement using object detection. So we have to determine the distance between the vegetation and the power lines and determine whether it would be safe. So first we need to collect a data set of images and train our model to be able to determine whether it's safe or not. Then we're going to need to identify perspective and calibrate the measurements. So that'll be used using OpenCV from our images. Then we wanted it, and then lastly, we'll just be able to determine how far the surrounding vegetation is from the power lines. And then we classify into two categories, danger or no danger. So to give more of a detailed explanation of what is danger. So PG&E's current guidelines for power line safeties are as follows. So it's 18 inches in non-high fire threat areas. So that's like not California or Texas. And as well as 4 feet in high fire threat districts, with 12 feet recommended at the time of pruning to maintain the clearance year-round. The autonomous drone will be able to detect any clearances that do not meet the guidelines of the PG&E, as well as communicating a lower risk threat with around 5% greater than the clearance distance.
So for both of these methods, we need data sets, and for those data sets, we need to find a bunch of images, right? But the thing is, we don't have a lot of access. So what we've turned to is using generative AI to create certain images in our models, in addition to the real life images we found. So this method really helps us get many more images. But I feel like the downside to this is that it takes a lot more tries to find the correct images that fit our needs. But overall, it helps us get the amount of images that we need. So on the right hand side, you can see two examples. One is an example of an AI generated image of trees not intersecting with power lines, and the bottom one is an image of an AI image of trees intersecting a power line. So far, some of the roadblocks and possible challenges we've faced is that there are so many factors to consider when you're determining a fire risk, and we can't really get all of them because inspecting it with a drone is pretty complicated. In addition, a normal camera might have a lot of trouble inspecting the areas with congested with trees. So what our plan is to overcome this roadblock is to get specialized cameras that can I guess have a better width and can see a lot better through those congested trees. In addition, determining tree stability will have to be analyzed by many other metrics, not just the camera. So determining that tree stability might be a little more difficult. And bad weather conditions such as like high wind or fog will lead to low visibility for our cameras, meaning that our data might be like corrupted and might not be as good. So we have to figure out how we're gonna combat that. And overall, like good images are proving hard to gather. Our AI generation is helping a lot, but I feel like we still don't have that level of images that we need to overcome all our like problems. So some of our future actions is that like once we finish building our drone, we want to go test it for a stable flight in local parks. So we make sure our drone is, stable. So when we actually go out and try getting data with our drone, we know it's like reliable. We also plan to collect pictures using our drone once we check that it has stable flight and it's reliable. And once we do that, I think that's another way we can overcome that roadblock I was talking about not having enough images. And once we finish building our machine model, we hope to obtain like a license to fly a drone in public places. So we can fly our drone in rural areas like state parks and other rural areas. And in addition, our Holy Bro drone has autonomous flight capabilities, which we plan to incorporate for additional convenience in a broader use case. But currently, I think we're just trying to first get our drone into the air with stable flight. So we would really like to acknowledge ASDRP for providing our the lab and the means to work on this project. And thank you to Dr. McMahon for supporting and providing a really valuable insight for this project. So here's our kind of literature review and sources. These were really helpful when we were first starting off and seeing like what really like affects like fires, like how we could build our machine model and so on. Does anyone have any questions?